How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And we come now to another lesson in the dramatic subject of sound, and this one possessing some uncommon enchantment. You remember, I hope, that I have considered plates fixed in the middle and bowed with a bow, and certain figures result due to the behavior, the mode of oscillation, vibration of the plate. And we call those plates Chladni plates, capital C-H-L-A-D-N-I, and the figures that result when the plate is bowed, Chladni figures. Now, a little different matter. I have a rigid support from which I fix two strings in this manner, and at their common junction, a third one, and hanging remotely at the bottom from the third one, a funnel in which I put some sugar or sand or salt. This physical arrangement is known as a Blackburn pendulum, after a Scot by the name of Blackburn, and it has marvelous vibrational properties. Depending upon the lengths of these strings, the length of that string, and this distance here, a matter which calls for some mathematical exploration, and I won't go into that. But if now I draw this pendulum bob aside, having filled it, say, with salt or sugar, it oscillates in a very pretty way and makes some figures which are called Lissajous, L-I-S-S-A-J-O-U-S. Lissajous figures after a Frenchman who made an exhaustive study of them. So let's go over here and see this Blackburn pendulum generating the Lissajous figures. Here is a framework, looks rather like a guillotine. Here are the two strings symmetrically fixed. Here is the junction of the third, and this bob I could move up or down, making this length less or more. And I'm going to fill this funnel with some salt, keeping my finger over the open end. I have, by the way, put some lead weights around this funnel to make it heavier, to give it larger inertia. Now I'm going to draw this off in some arbitrary way and let it go. Now watch what happens. I say that's beautiful, beautiful. Now its motion is damping out, that is, getting less and less in amplitude, and notice the pretty figure that results. Now, let me fill it again. Let me fill it again. And let me change this position. Oh, I may have a little trouble here. I need several hands. Let me change the position. There, I've gone way up there. Well, no, with only two hands, I can do just so much. So let it slip out. No hurt. Okay. Now I'm going to start it again in another position. Watch it. We should, I suppose, get rid of this figure in order to see subsequent ones, but you'll get the idea. Well, I'm having a little trouble, perhaps because the framework has some motion in it. But anyway, these are very pretty things to see, and I want to show you what can be done with this apparatus. Instead of having a funnel with sugar or salt or sand in it, let me have an enormously heavy ball with a hole in the ball and a light lodged inside the sphere, the ball, so that a point source of light falls on paper. This paper I could have on the turntable of a phonograph. So the table turns, the ball moves, and the light describes some beautiful curves. Let me show you some. They are absolutely enchanting. Here's one. Look at that. This is a Leisure Zoo figure made by a heavy bob with a light inside. Here is another one. And they are absolutely enchanting and of highly artistic composition. One would hardly imagine that these can be done by so simple a mechanical device. Look at that. Oh, here's one that I nearly missed, which would be a shame, really, to miss. This one needs to be viewed more properly that way. Or one such. Look at that. Or, look at this one. Incredible designs. Or such. Incredible. Oh, let me turn that so the camera gets a better view of it. And finally, such a one as this. Beautiful thing to witness. Now, one of my students of earlier years made such a device, and instead of having a funnel with sand or a ball with a light, he had a heavy ball with a pin attached. And the pin moved, and the paper moved. And here are some of the figures that resulted from his work. Notice the beautiful composition. Yeah. I'll run through these quickly to suggest the beauty, the artistry that can result from such an investigation. Lizard figures. Compounded harmonic motions. Lizard figures. Very dramatic. More to our business. I have here a glass tube in which is lodged some very fine cork dust. And here is a metal rod which I have clamped at the very middle. Half of the rod is in the glass, nearly, the other half beyond the clamp. And on the end of this rod is a piston. I'm going to draw that for you. Here is the glass tube. It is stopped up on this remote end. Here is the rod inside. It is clamped about there, and it has a piston right here. I suppose this is the piston rod, and yeah, that's piston. Now what have I done? Some cork dust, metal rod. I am going to stroke the rod with a resined or rosined cloth so that the cloth grips the rod and lets go, grips and lets go, quite like a violin bow grabbing and letting go of a string. We call this relaxation oscillations. You can do this sometimes with a cane. You push the cane on the sidewalk, it skips and grabs and skips and grabs. Relaxation oscillations. And what will happen? A compressional pulse runs down the rod, which is shaking like this, bounces off the end of the piston here, reflects from the cork stopper, and if things are right, we see the cork dust gather in very sharply defined little places, and thus we could determine the velocity of sound in this metal rod. Let us get a view of that. Let us get a view of that. Cork dust, rod, watch. We have to get tight on it. It's a little difficult to see. Perhaps the camera can get another view of it. Oh, there is some motion there. I'm getting tired. That's hard work to do that. Now, what did I say we could do? With this, which is known as Kunsttube, K-U-N-D-T'-S, we can determine the velocity of sound in the metal rod, or we could put some unknown gas in here, or a known gas, say carbon dioxide, and determine the velocity of sound in the carbon dioxide. One more demonstration. I have suggested that an acoustic wave is a compressional wave that advances from here successively through the air and falls upon your ear. To represent the advance of such a compressional pulse, I have here a little rig which I could name a wave machine. Here are two strings supporting the ends of a little bar magnet. There is a bar magnet, many bar magnets, and they are so aligned that their like poles are adjacent. Now, magnetically, you know, magnetostatically, like poles repel. I'm going to remove one, let it fall upon the others, and watch the compressional pulse advance. Watch it now. There it is. And watch it now reflected, and here it is. This reflection from an open end, a very important idea in physics. Let me suggest it once more. Right. I return again. Yeah, I returned once, so I return again. To this subject of quieting an electric cable which is swinging too much. This one that I have shown on an earlier lesson is an American design. Very useful physics. I have here one made by the Germans of a little different design, and a third one made by the Swedes. And you see the cable goes through here, and this swings like that and like that, taking up the energy of the cables. One more sound producer. Notice how absolutely simple and trivial the subject can be. A piece of masonite, a prismatic slab fixed to a string. I think it is called a bull roarer. All I'm going to do is swing it around like this, and it's going to make a sound. And if you have seen some of the earlier lessons that I have done in physics, you will recall Bernoulli's principle, which is why a flag flutters, which is why this does what it does. Listen. A bull roarer. And it seems appropriate because the subject is so absolutely enchanting to show you once more a vibrating plate, which I will do with all speed. A plate which I have sprinkled, and I say that is very enchanting to see. And I thank you for following our discourse on waves and sound. Let me show you one more. Let me show you one more. I sprinkle it. Now. And this is beautiful for you to remember, and I thank you once again for following our discourse.